Hi, and welcome to the fourth lecture of this computer vision course. Last time we discussed sparse 3D reconstruction techniques, how to, based on sparse correspondences or features, reconstruct 3D structure sparsely from two or more views. The topic of today is dense stereo reconstruction, which is how we can obtain a more dense 3D reconstruction from just two images if the camera intrinsics and the camera extrinsics, the camera poses, are already known. This lecture is structured into 5 units. In the first unit, we are gonna cover some preliminaries to the following units, including how to bring the images into a suitable configuration such that matching is fast, and also how to obtain depth from the actual measurements, the so-called disparities that we are actually estimating using these stereo algorithms. In the second unit, we're going to discuss the most basic dense stereo matching algorithm called block matching. And then we move on to algorithms that use deep neural networks, so-called Siamese networks. We also cover spatial regularization, how to overcome some of the ambiguities that are present in this problem, and finally cover the more recent end-to-end learning approaches that require a lot of data but produce state-of-the-art results today. Okay, so let's start with the preliminaries. How can we actually recover 3D from an image? In general, this is of course an ill-posed problem, but there are several cues. If we look at an image, for instance, what we can look at are occlusion cues. If we look at this image here on the right, then most of us will probably say, well, based on this configuration here, the object, this vertical object here, is in front of this horizontal object in the back. Now, this is a mechanism that has been exploited by artists, and you're probably all familiar by the famous Escher paintings. So this is one cue, how to obtain 3D structure from an image. Another cue is parallax, and that's closer to the stereo problem that we're going to discuss today, but it's also something that you can obtain from one image alone, where if you look at an image and you see that an object is moving relative to another object, for instance, by seeing a mirror reflection of that same object, then you know that these objects can't be located at the same depth. So for example, here we have this pole with the lamp on top, and we have the moonlight, and so they are clearly displaced here, while in the mirror reflection they are co-located. And this is called parallax, and this principle is also used in stereo that we're going to discuss today, but using two cameras. Another cue is of course perspective. If we look at an image and we know that some things in that image are parallel, then we can infer something about the perspective effect and also the depth. Then one thing that we can also use is so-called accommodation. Accommodation means focusing on a target, because we do have lenses that are not sharp everywhere. We as humans need to actually focus on a specific object. And if we focus on a specific object, then two things happen. One thing is that we have to adjust the lens, and in the human eye that's done with muscles. As you can see here, there's two different configurations on how the lens in the eye is stretched. And because there is receptors inside these muscles, we can recover a signal on how these muscles are actually, what is the state of these muscles. And that's also something that goes into, of course, the focusing process. So we can measure the focus state of the lens. And the other thing that happens is that different areas in the image, if focusing on a particular point, get blurred differently. So if I look at this point here, then maybe the background gets blurred. And now this effect can also be used in an artistic manner. For instance, in this example, where if you see this image and I ask you, is this a real image? You will probably tell me, well, it looks like a real image, but it's more likely to be a toy scene, something that you would observe when looking at a toy scenery through a big lens. And that's true because the lens that you would need in order to create such a depth of field effect as we can see here would be insanely large for a real scene. So this effect here has been synthetically created, and it's actually a real image that is sharp everywhere and has been captured with a relatively small aperture compared to the scene. And then finally, what we're going to talk about today is stereopsis, where we use the principle of triangulation and take an image of a scene from two different locations, from two different viewpoints, and by observing points in the scene move differently far, by observing this parallax effect, and by knowing the location of the cameras, we can then triangulate that point in 3D. We can follow these rays and see where these rays intersect, and that gives us the 3D point. Now, why is binocular stereopsis a good idea? Well, there is some examples in history of species that do not have two eyes. There's some species that have more than two eyes actually, and there's some very rare cases like here that have only one eye, but in general most species have two eyes. And so it seems like this is an established system. It's the minimal configuration with which we can perceive depth relatively robustly. And so that's something that we probably also want to exploit if we want to make machines see. There's also some examples where the principle of stereo perception has been exploited in a special way, in a way that the so-called baseline, which is the distance between the cameras, has been artificially enlarged in order to obtain a better depth perception. Remember that when you do triangulation, then the larger the relative viewpoint, the more precise, the more certain the triangulated 3D point is. And so if you put the cameras further away, or if you put the focal points further away, then you will get a better sense of depth. And that has been, the principle has been used by the stalk-eyed fly and also by these devices like the stereoscopic rangefinder that has been used in also in the military in order to determine the distance of a target from the observer by adjusting prisms in this tube in order to triangulate distance. Now here in this course we are gonna covering the estimation of depth, or equivalently disparity, which is inverse depth. Disparity is the relative displacement that we observe between pixels in the two images that we have captured of the same static scene. And we're trying to do this as densely as possible. So the goal is that ideally for every pixel that we have in the input image, let's say in this reference left image here, we want to find a depth map that's color coded in this disparity map here on the right hand side. And as you can see in this case, the scene has not even been captured at the same instance in time, but the majority, the large parts of the scene are static. And so that the majority of the scene can be reconstructed despite the fact that there is some people here moving around. Now, given that we have reconstructed such a displacement map, such a disparity map that we're going to talk about a lot in this lecture, we can of course also recover the depth because it's basically just the inverse of the disparity, as we will see. And then we can take all of these pixels for which we have such a depth value obtained, and we also know the color value because we have the color in the reference image, and then we can project this into a 3D point cloud. And for this particular example, this has been done with a very old stereo algorithm that we have been publishing more than 10 years ago. It's actually a real-time algorithm, was already real-time in 2010. We obtain a 3D reconstruction like this. This is a reconstruction that's relatively dense and comparably precise, at least at the time, while being real-time and covering the majority of the scene, and only being reconstructed from these two images. So, to summarize, what is the task? What is the goal? We want to construct a dense 3D model from two images of a static scene, or a mostly static scene. Alternatively, we can take two images at the same point in time if we can synchronize the cameras. For example, in a stereo sensor that's mounted inside a vehicle. Many modern vehicles have cameras inside, and some of them do have stereo cameras. These cameras are triggered electronically, such that they capture the scene exactly at the same point in time. And then, of course, the scene is, at that point in time, it's static with respect to the two cameras. So the pipeline is as follows. We first calibrate the cameras intrinsically and extrinsically, as we discussed in the last lecture. Then we rectify the images given this calibration. And what rectification means, we're going to discuss today. It's basically the process of bringing the images into a format that's more easy to process using these stereo matching algorithms. And then we compute this displacement, this disparity map for the reference image. For every pixel in the reference image, we ask, well, how much does this pixel have to move how much does this pixel move in order to land on the new location in the right image, in the target image? How much is the pixel displaced between these two images? Then typically there's a step that removes outliers using some consistency or occlusion test. And then we can obtain the depth from the disparity using the parameters of the camera. And finally, we construct a 3D model, for instance, via a simple concatenation of the 3D points. That would be the simplest method, and meshing them, or via more advanced methods such as volumetric fusion and meshing, as we'll discuss them in lecture 8. Then let's see how such a stereo matching algorithm at a broader level could be integrated into a bigger system, into an entire 3D reconstruction pipeline. So what do we do here? We have not just two images, but a set of input images from which we want to obtain a 3D model. And then a typical procedure is as follows. We take these images and we compute the camera poses using incremental bundle adjustment, let's say, as we discussed in lecture 3. And then once we have the camera poses and we know which of these views are adjacent to each other, we can compute dense correspondences, as we'll discuss in this lecture, for each adjacent view using the Apipolar geometry that we know then once the cameras are calibrated. And so we get depth maps for each of the images. And these are 2.5D representations. So in order to combine all of these into a 3D model, we can use algorithms such as depth map fusion that lead to a coherent 3D model where we can extract a mesh that takes into account all the observations that we have made. So the topic for today is really this part of the pipeline, where we assume the camera has been calibrated intrinsically and that also all the camera poses have been estimated precisely, which is typically the first step. And then we can go and start and find adjacent views and try to do dense stereo matching across adjacent views. If we do this for two images, as discussed in this lecture, this is called binocular stereo matching. If we do it for more than two views, and we'll discuss this later in the lecture, this is called multi-view stereo. So both options exist. Using only two views is a little less precise, of course, is a little bit more ambiguous, but it's typically faster. So both problems are heavily researched still in the community. And then a final model could look like this. This is a very old model that we have produced, and it's a model that has been produced by simply stacking all the point clouds together, so no sophisticated fusion algorithm. But you can already see, you can already get a pretty good idea of what the 3D structure should look like. And it's grayscale because these were grayscale cameras. You can see these little triangles here, these red triangles here are the camera poses, illustrate the camera poses that have been used. For each of these camera poses, we have estimated depth map. This was done using a stereo camera. And then we have accumulated all the point clouds into a larger 3D reconstruction. Okay. Now, something that's really important for performing dense stereo reconstruction is that we know the apipolar geometry. And that's what we have discussed already in the last lecture. And let me just recap that with a single slide. So here on the right is an example of an apipolar geometry where we have the apipolar plane that is connecting the 3D point projected onto both of these image planes. And the 3D point is projected to the left image plane with or via camera calibration matrix K1, to the right image plane via K2. And then once we have estimated the apipolar geometry, which can be expressed by the essential matrix E tilde, which is a homogeneous matrix, image correspondences expressed in homogeneous coordinates are related by this simple expression here, x2 transpose E x1 equals 0, where these x tildes here are the ray directions, where we take the pixel location and multiply with the inverse of the intrinsic calibration matrix K for each of the cameras. And then one important property of this apipolar geometry is that the correspondence of any pixel x1 in the first image is located on the apipolar line in the second image, and that apipolar line is given by the essential matrix multiplied with that point in the first image, or the viewing direction to be more precise. And then vice versa, the correspondence of some point x2 must be located on the apipolar line L1 in the first image. And then also the apipolar lines intersect at the apipoles. So here's another example where the 3D point has changed. We can see how this plane forms a pencil of planes, and all of these planes actually pass through the apipoles, which means that also all the apipolar lines pass through the apipoles. That's what we have discussed last time. Now, the most important property of the apipolar geometry that we're going to exploit today is the fact that I've just mentioned, that if I take a point in the left image, call it x1, and I want to determine where that point is located in 3D space, if I want to triangulate that point, and I have to find the correspondence of that point in the right image in order to do so, then that correspondence must be located on the apipolar line. So instead of searching through the entire second image domain, we just have to search along the apipolar line. Remember that if we don't know the relative camera poses, we want to estimate the apipolar geometry, then we don't know this property. So then we really have to do sift matching, for instance, to all possible feature locations in the right image. But now we just need to search along the apipolar line, and that's much more efficient. So now we can do this densely. We can query for every pixel in the left image, all pixels along each of the corresponding apipolar lines in the right image, and find the best possible pixel that in some form, as we'll discuss later, corresponds best to that pixel that looks most similar to the pixel in the first image. And this reduces the correspondence search problem to this much simpler 1D problem. So as an example, for VGA images, if we wanted to, for that point here, for that pixel here, we wanted to find the correspondence in the right image, and we wouldn't have such a simplification to a 1D search constraint, then we would have to search for all the pixels in the right image, which for VGA resolution would correspond to 300,000 pixels. So we have 300,000 hypotheses that we need to do a comparison to in terms of little image patches, let's say. Now, if we just have to search along the apipolar line, and let's assume the apipolar line is roughly horizontal, then we have roughly 640 pixels only. So a factor 480 less computation, which is significant, of course. Now, one important concept that we'll introduce in this unit is image rectification. What happens if both cameras face exactly the same direction, which means that the image planes are lying in the same plane, in the same 3D plane? In other words, the image planes are coplanar. What that means is, you can already imagine what's happening then, is that the epipoles, they will not lie inside the image domain anymore, because the baseline obviously can't intersect the image planes anymore, because the baseline is now parallel to these two planes. So what happens is that these epipoles, E and E prime, or E1 and E2, they go to infinity, and all the epipolar lines become parallel to each other. And if we do it right, they also become horizontal. So they become parallel to each other, horizontal. So we just have to search now correspondences along image rows. And this significantly simplifies implementation. We don't have to search across slanted lines, across slanted epipolar lines in the target image, but we can search along image rows, which is much simpler to implement. And that's why rectification is important, and rectification is typically applied in order to make these stereo matching algorithms, binocular stereo matching algorithms. It's only working for 2 images. Can only do this for 2 images unless all of the cameras are located, all of the camera centers are located on a line. Otherwise, you can't do that for more than 2 images. But if you have 2 images, then you can exploit this property, and that's what almost all binocular stereo matching algorithms do. Now, this is nice, but it's very difficult to actually manufacture a stereo setup where these cameras are exactly facing the same direction, because just a slight deviation from that direction, which is easy to introduce by just some mechanical slack that is introduced, is already resulting in a couple of pixels error. And so matching along apipolar lines will not work anymore, because the apipolar lines are shifted by a few pixels, and so the patches will not align anymore. And these matching algorithms are very sensitive to that. So you need to really make sure that these apipolar lines are really pixel accurate or subpixel accurate. So what can we do if the cameras or the images are not in this required setup? Well, the nice thing is that there is a trick. We can actually rewarp these images through a rotation that maps both image planes to a common plane parallel to the baseline. In other words, we can bring the non-rectified setup into a rectified setup, and this process is called rectification. And the nice thing about this is that for this rotation around the camera center, because we're just rotating the camera into a new virtual camera around the camera center, the optical center, these 2 points here, we don't need to know the 3D structure. Similar to where we have estimated homographies for stitching panoramas by taking pictures from the same location and rotating the camera, this is also just a homography that we can apply here, a rotation homography. So without knowing the 3D structure, which we don't know, we can actually warp the images to bring the cameras into this rectified setup, which is really nice. So here's an example. So this is the setup from before, and now we are rotating these cameras virtually by warping the images such that the epipoles move to infinity and the epipolar lines become parallel and horizontal. So here we have the epipolar line for x1, for example, lies on the same image row as x1 in the other image, and the epipolar line of x2 lies on the same image row in the first image. Now, how does this work? How can we make epipolar lines horizontal? Let's first look at a simplified scenario. For that simplified scenario, let's assume that both calibration matrices and the rotation matrix are equal to the identity matrix, and that the translation vector between the two cameras is just a vector in x direction. So from the left camera, from the first camera, we go t millimeters or meters into the x direction, but then the other coordinates, the y and the z coordinates, are empty or are 0 for that translation vector. And so in this, what we want to confirm now is that in this simplified setup, this is the goal, the epipolar lines are actually horizontal. This is already the rectified setup. If this setup would occur, then we would be done. For this particular case, the essential matrix is very simple. Remember, the essential matrix is the cross product between the skew symmetric matrix corresponding to the cross product matrix of the translation vector times the rotation matrix. And because the rotation is the identity, this becomes just this skew symmetric matrix. And because this vector here is very simple, this matrix looks like this. All the entries are 0 except for this x components. Now, as the calibration matrices are the identity matrix, two corresponding points in augmented vector notation are related by this epipolar constraint. Remember again from the previous lecture that we had x tilde here and x tilde 1 here, because we assumed that there is an arbitrary calibration matrix, and so we have to compute x tilde by multiplying x bar with k inverse in order to get the direction. But here we don't need to do that because the calibration matrix is already the identity matrix, so it's a very simple setup. So we can directly write x bar here. And otherwise this is simply the epipolar constraint, which must be 0. Now if we plug in the essential matrix now here, we obtain this expression here. So here we just multiplied x1 with this matrix, and this y1 here indicates the y component of the first point. So this is the second element of that x bar 1 vector. Now we multiply x bar 2, take the inner product with this vector, and again we denote by y2 now the second element of that vector. So the first element is multiplied with 0, the second element, which is y2, gets multiplied with minus t, and then the last element of this augmented vector is 1, of course, gets multiplied with t and y1. So we're left with this expression t y1 minus t y2, and this expression must be equal to 0 because it must satisfy the epipolar constraint. So what we see here is that for this very simplified setup that we have constructed artificially, y1 equals y2. So in other words, the two images of the 3D point, the projections of the 3D point x, must lie on the same horizontal line. They are on the same scan line, on the same image row. The projections of the 3D point are on the same image row. This is the rectified setup. Now, what if this setup is not the case? How can we take an arbitrary setup and rectify that setup? Well, in order to rectify an image, we can just rotate, we can compute a rectifying rotation matrix that rotates these cameras virtually such that this particular setup here is fulfilled. And what do we have to do? Well, we have to, of course, align the x-axis of the camera coordinate system with the translation vector. So that must point to the other camera center, or to the epipole, in other words. And then we want to introduce as little distortion as possible to the other two axes of the new camera coordinate system, of this virtual camera coordinate system. And of course, the camera coordinate system must always be a proper right-handed coordinate system, so all the coordinate axes must be perpendicular to each other. And with these constraints, we can now calculate this rotation matrix. This rotation matrix is simply what we have parameterized it by the vectors R1, R2, and R3, which are the rows of that rotation matrix. Where, yes, the rows of the of this matrix, where R1 is simply pointing into the direction of the translation vector, but of course this translation vector magnitude must not be equal to 1, so we have to normalize it to obtain a proper unit vector. And then R2 is the cross product of the c of the vector of the c coordinate of the original camera coordinate system with the first vector that we have computed in order to compute the y coordinate of that camera coordinate system. And then the third coordinate, the c coordinate of this new camera coordinate system, must be the cross product between the first two, because otherwise it wouldn't be perpendicular. Right. So this is one choice. There's more choices, but this is the most this is the simplest and the best choice if the cameras are already roughly aligned. And we'll see an illustration of this on the next slide. Now, as the epipole in the first image is in the direction of R1, it's actually easy to see that the rotated epipole is an ideal point. For that, we can simply multiply R1 with this rectifying rotation matrix, and because the first row of that matrix is R1, and because R1 has magnitude 1, we get a 1 here, and because these other two coordinate axes are perpendicular to R1, they are 0, which means we have an ideal point, a point at infinity for the epipole after rotating it with the rectifying rotation matrix. Right, it's a homogeneous vector that has a 0 as the last element, and that means it lies at infinity, and it lies at infinity in the x direction because it has a 1 here in the x coordinate. So it's an ideal point at infinity in x direction. Therefore, applying this rectifying rotation Rrect to the first camera leads to parallel and horizontal epipolar lines as desired. So here's an overview of the entire rectification algorithm. We first estimate the essential matrix, then we decompose it into T and R and construct Rrect as above. We warp the pixels in the first image, then using this expression, we take the inverse of so we take a pixel in the first image, then we compute the inverse of the calibration matrix in the first image, and we apply this rotation, and then we take the calibration matrix of this virtual camera, which we can decide arbitrarily in order to obtain this projected point. And similarly, we can do this for the point in the second image, except for also taking into account the rotation between the first camera and the second camera, the extrinsics, basically. Because we also, I mean, this overall rotation is, of course, a rotation that's combining the rectifying rotation of the left camera plus the relative rotation between the left and the right camera in order to have both of the image planes being coplanar after this warping. Little remark, K is a shared projection matrix. It must be the same. but it can be chosen arbitrarily. Typically, this is chosen such that it's close to one of the calibration matrices, let's say K1. And in practice, we don't compute this transformation, but we compute the inverse transformation, because taking all the pixels in the original image and projecting them into the virtual image is not ideal, because there might be points, I mean, that get projected on top of each other, and points that get stretched, so there is a missing pixel then in the target image. So what's better to do is to go through all the pixels in the target image, in this new virtual image, and then query the source pixel in the original image by applying the inverse transformation. So we just invert this expression here. And then this point will not necessarily lie on an integer location, of course. So what we do then in the original image is we do an interpolation, like bilinear or trilinear interpolation, not bilinear or bicubic interpolation, or some other interpolation technique, in order to find the RGB color value that we have to insert at the target image, for which we have queried the source. So here's again a graphical illustration of this rectification, of the calculation of the rectifying rotation matrix. Let's assume we want to compute this for the camera 1 and then adapt camera 2 accordingly based on this equation here, which includes this additional pose rotation R. So we have the camera centers here. I didn't draw the second camera because it's irrelevant here. We have the principal axis, that's the C axis of this camera. And we can see here that the epipolar line is not horizontal in the image, but is slanted. And the epipole is in the image domain. So what we do now is we compute, this is the desired new x-axis of that new coordinate system, which we compute as the vector that's pointing into the direction of the second camera center. And then we compute the cross product of the C direction of the original camera system and this new vector in order to obtain the new y coordinate of the new camera system. And that makes, by doing this, we make sure that we introduce little distortion, that the camera is oriented roughly the same way, because we could also rotate the camera with an in-plane rotation, but we don't want to do that. We want to make introduce as little distortion to the original image as possible. And then we have the third coordinate, which is perpendicular to the first two. So we have computed x, y, and z coordinate of the new camera coordinate system. This is the rotation that's applied to this original coordinate system. And by doing that, we obtain a new image where then the epipolar lines are horizontal. Here's an example. On the top, we see this is actually, on the left is the right image, on the right is the left image, but it doesn't matter. So here we have an example where we see the epipolar lines before rectification, and at the bottom you can see the perspective transformation, the homography that has been applied in order to warp these two images such that the lines that we see above become parallel to each other and horizontal in the image domain. And if we look at a particular point in this image here, we find that point along this epipolar line in the other image. This would be the correct correspondence. But if we do this in the rectified setup, we just have to search along a single image row. So correspondences are located on the same image row as the query point. Here's another example of a rectified setup. I show you here the first image, and this is the second image. And what you can see is, if I toggle between these two images, that points that are far away move little, and points that are nearby, like this point here on the car, the backlight, move more. And this motion of the points is called disparity. And because there's this relationship of points that are close to the camera move a lot and points that are far away move little, we can estimate the depth from the disparity. There's actually an anti-proportional relationship between disparity and depth. The depth is actually proportional to 1 over the disparity. Here's a illustration of a depth map that has been estimated by some algorithm, where you can also see with this color coding here at the bottom that points that are far away have little disparity, they move little, and points that are nearby here in the yellow and green and red regions, they have a larger disparity. In this case, the pixel motion is between 0 and 160 pixels. Actually, pixels move to the left, right? So if we look at the left image here, and then we look at the right image, then a pixel in the left image has moved from its current location to the left. But we typically count this disparity still as positive disparity values despite moving to the left. Now, given that we have these disparities calculated, what we want to do is we want to recover the depth from the estimated disparities. And what we know now in this rectified setup, which is quite nice, is that the left and the right ray must intersect as both lie by definition on the apipolar line. Because we're searching along scan lines, these rays must intersect because we are searching on the same apipolar plane. And so in this particular setup where both, here we have the cameras again, now in a bird's eye view, we don't show the y coordinate, just x and c. And we have the image plane and the camera centers of the left and the right camera in this rectified setup where the camera planes are parallel to each other. And there's a 3D point at distance c. And we have now the disparity, which is the combination of x1 and x2, which is the relative displacement in the images from here to here, basically, if we would toggle between these two images. And now, because we have this very simplified setup, also the depth estimation becomes a very simple formula. Now, assuming the disparity d being x1 minus x2, so we have x1 here and x2 is actually negative. So the disparity is, let's assume this would be 10 pixels and this would be minus 10 pixels, then the disparity, the displacement would be 20 pixels. Then the following relationship holds. We look at these two triangles, these equal triangles, red and blue. The blue triangle gives us the following constraint. We have c minus f, this is this, minus this, is basically this distance here, is equal to c minus c minus f, which is this distance, divided by b, this is the baseline, minus the disparity, which is actually this distance here. So we have this divided by this is equal to the entire c here divided by the entire baseline b, because these are equal triangles. Now we can slightly rewrite this equation by multiplying on both sides with the denominator and by solving for c. And so we see now this anti-proportional relationship that c is actually proportional to 1 over the disparity. The depth is proportional to 1 over disparity. In particular, it's equal to the focal length of the camera of this rectified setup, of this new virtual camera matrix, times the baseline, which we know from the extrinsic calibration, divided by the disparity that we estimate using a stereo algorithm discussed in the next units. What's particular about disparity estimation is that actually the depth error, delta c, grows quadratically with the depth, which leads to the fact that if we estimate depth from these disparity maps for very far away objects, we are very imprecise, while if we estimate depth for objects that are close, we are very precise. The proof of this is very simple and will occur in the exercise.